Today we're going to talk about ionization energy and electronegativity, two concepts that chem students get confused a lot.
The visuals go kind of fast, so feel free to pause the video anytime you need. Ionization energy is the amount of energy required to remove the most loosely bound electron, the valence electron. Here we have Lydia lithium and Francesca fluorine. Lydia lithium has a very low ionization energy. Thus, it's very easy for Francesca fluorine to take her most outer electron. Francesca fluorine, however, has a very high ionization energy, so it's super hard for Lydia lithium to remove her outermost electron.
Electronegativity is the tendency of an atom to attract an electron pair toward itself. In the video, two atoms playing tug-of-war over a pair of electrons.
Francesca fluorine wins because it's much more electronegative, which means it's much better at gaining electrons than Lydia lithium. While these may seem like pretty opposite concepts, they have the same general periodic trends. Both ionization energy and electronegativity increase from left to right across the periodic table and decrease as you go down each group of the table. But let's break it down as to why.
Ionization energy, simply put, is the energy associated with losing electrons, increases across the periodic table because effective nuclear charge increases from left to right. Let's quickly break down what effective nuclear charge is. So, effective nuclear charge is the net amount of positive charge experienced by valence electrons. As we go across the periodic table, the amount of protons in the nucleus increases, while the amount of electrons in the inner shells, or the shielding electrons, stays the same. So, the valence electrons feel more and more attraction from the nucleus. Thus, ionization energy increases from left to right along the periodic table because the electrons are more attracted to the nucleus and thus harder to lose.
Electronegativity, simply put as an atom's ability to gain electrons, increases from left to right for the same reason. The increasing effective nuclear charge makes electrons easier to steal because those electrons are more attracted to the nucleus of an atom with a higher nuclear charge. So they will naturally migrate towards that atom, as opposed to one with a lower effective nuclear charge and attraction ability. However, this trend falls flat at group 18, the noble gases, which have an electronegativity of 0. This is because noble gases are already stable, with completely filled S&P sublevels, so gaining another electron would create a higher energy level that would not feel the attraction from any protons in the nucleus, which is unfavorable not only to the atom, but to any prospective electron.
However, as we move down the periodic table, ionization energy decreases because atomic size increases. Each additional atom, as we go down the group, has an additional energy level. Each additional energy level makes it so that the outermost electrons are farther away from the attraction of the nucleus, thus making them easier to remove from the outermost shell and decreasing the energy required to do so, which is the ionization energy.
Once again, electronegativity follows the decreasing trend as we go down a group in the periodic table for the same general reason. Increasing atomic size means that any additional electron gained would be further away, and thus feel less attraction from the nucleus. This situation would be unfavorable to any electron, thus lowering an atom's tendency to gain those electrons because they generally wouldn't choose to migrate to such an atom. One thing that ionization energy has that electronegativity doesn't is exceptions to these trends. One exception falls between groups 2A and 3A. Although ionization energy generally increases from left to right, beryllium has a greater ionization energy than boron. This is because boron's outermost electron falls in the p sublevel, while beryllium's only two valence electrons fill the s sublevel. This is important because there is a lower probability that boron's unpaired electron will be close to the nucleus, due to the way that p orbitals are shaped in comparison to s orbitals. The fact that beryllium's outermost electron has more potential to be closer to the nucleus makes it harder to remove than boron's due to the increased possibility of attraction, thus making boron's ionization energy less than that of beryllium's outermost electron, despite the general trend. A second exception to the ionization energy trend falls between groups 5A and 6A. The ionization energy, for example, of nitrogen is actually more than that of oxygen. This is because nitrogen's valence electrons have filled the p sublevel with each in their own orbital and are more stable. In comparison, oxygen has one more valence electron that must share an orbital with one of the other three, and thus the electrons are altogether less stable because the shared orbital has repulsion. This repulsion makes it easier to remove oxygen's outermost electron, and thus it has a lower ionization energy, because removing that electron would make it more stable. Now let's go through a couple of review questions to see how well you retain the information. Question 1. What is the fundamental difference between ionization energy and electronegativity? Go ahead and pause the video to figure this one out. Okay, this one's pretty short and simple. Ionization energy is associated with losing electrons, while electronegativity is about gain. Question 2. Given magnesium and aluminum, which element has the greatest first ionization energy, and why? This might seem like a trick question, but we just talked about it. Magnesium is a group 2A element, and aluminum is a group 3A element, so they have an exception to the general increasing rule. Magnesium actually has a greater first ionization energy because its outermost valence electron is in the S sublevel, which has a greater probability of being close to the nucleus compared to the location of aluminum's outermost electron in the P sublevel. Thus, magnesium's electron is harder to remove because it likely feels more attraction to the nucleus than aluminum's valence electron. We hope you learned something about ionization energy and electronegativity. Thanks for watching!